class said they want to add math as another major. I'm like, oh, I thought class went really poorly yesterday, so maybe I was wrong. What in the world?
Is it second major?
I think my dad is having a stroke with the last two emails or texts he sent me.
For like half a second, I thought you were
I
serious.
thought
you were serious. I was like, oh.
No, I hope not.
Okay. Oh.
My mom just got out of the hospital after being there for a week. So.
Is it 7? So it's like.
Oh, it's just got a weird random character. My guess is it's in his pocket.
Where we're guessing. All right. Oh, anyway, what questions do you have?
6, 10, 16, and 17.
Do you honestly have questions, or have you just not started it yet? Yeah. I kind of figured. I get that. Things are going okay, though? All right. So last time we talked about the first isomorphism theorem. We'll do another example of how we use it, but we didn't prove it, right? So let's prove it. We did not. So again, the first isomorphism theorem says that if we have a homomorphism from R to S, then if I take the ring R and mod out by the kernel of the homomorphism, I get something that is isomorphic to the image of the homomorphism. So kernel again is what?
The set of things that map to 0.
Yeah, the set of things that map to 0, and then the image is all the possible outputs, right? The way your book states it is that it's a surjective homomorphism. Well, the fact that I'm talking about the image makes it automatically surjective. Okay. All right, pardon me. So I want to show these two things are isomorphic to each other. We don't really have any other way to do it besides creating an isomorphism, right? You gotta find a function that maps from here to here that is one-to-one onto and preserves both operations. Both ring operations, right? So we have to show in order for it to be an isomorphism. What do things look like over here? What kind of objects are they over here? When we talk about the quotient ring, what kind of objects make up the elements of a quotient ring? Say again? Well, if we had typically not integers because these are a special thing. It might be in the side of these sets of integers, but just generally speaking, what kind of objects are in the quotient ring? Well, what kind of an object is the thing that looks like what's in the denominator, if you will? Say that again?
0, but that doesn't make sense.
Okay, so, but it's the things that we kind of treat like it's 0, right? That's the things that we treat like it's 0. In general, what kind of an object is this before we can even talk about doing this thing? What kind of a thing is that? It is a set. Okay, it's a special set. Special kind of set in a ring. You're just riffing, right? It's fine. Eventually you might hit the right word. We're talking about lots of different words. In order to be able to create this structure as a ring, this thing has to be a special type of set within the ring. Might be a synonym for like perfect or utopian. Ideal. Yeah, it has to be an ideal. Yes. Okay. In order to be able to create a quotient ring, I have to have an ideal to start with. What are the elements in your quotient ring then? What kind of objects are those? They are sets of things, but we give them a special name. The word set's actually in it. It's not so. But there is a prefix in front of set. It's the same prefix that you put in front of sign to talk about a different trig function. Yeah, they're cosets, yes. Okay. They're cosets. All right, so the things wrote in here are cosets, right? So remember, we create the cosets here. So elements over here look like an element that generates the entire coset, right? They look like that. We have a coset representative. There's lots of things in the coset, but we pick out a particular representative. What do you think we might want to map this particular coset to? Well, I want to map a coset over to something that's in the other set, which is the image of the homomorphism, right? I want to map that coset over to the image of the homomorphism. Well, what do elements look like in the image? Yeah, it's just the function applied to elements in R, right? So what do you think I might want to map this to over here to make sure that I land definitely in that image? So the function only takes elements of R. If you're on the right idea, it only takes elements of R. So I should take the function of all, yeah, the coset representative, right? So let's define a new function psi, I'll call it psi, of R plus I, and this will just be equal to phi of R. So psi here is going from the set of cosets to the image of phi, certainly. Now I have to be careful. This R plus I might be equal to, say, some S plus I, where R and S aren't the same element. What I mean by that is, for example, in Z6, the equivalence class of 2 would be the same thing as the equivalence class of 8, or the equivalence class of 14, and so on, right? These are all equal to each other, right? I'm taking a function on a coset and defining its output in terms of the coset representative. What I have to make sure I don't do is have that's something that's not actually a function. What I mean by that is I might have two different things that represent the same coset. I got to make sure that it has the exact same output when I'm done, right? For example, we talked about this a little bit ago. If you do something like make a function that equals the numerator of a fraction, you might have a problem, right? Because phi of a half would be 1, but phi of 2/4 would be 2, and now I don't have a well-defined function anymore, i.e. not a function. People say well-defined function. By definition, function is well-defined. Okay. It's either a function or not a function. Okay. All right, so what we have to show here is that this function that I just created is well-defined. That's the first thing I need to do. It's not clear that if I have two inputs that are identical, I have two outputs that are identical. So I need to check that to start with. So let's start with R plus I equals S plus I. Let's start with two cosets that are the same. Now let's remind ourselves what that means. That does not mean that R has to equal S, right? Over here, the equivalence class of 2 is the same as the equivalence class of 8 here, right? How do we know that these two things generate the same equivalence class over here in Z6? How do you know two things are equivalent mod 6? What has to happen? So if you subtract them and divide by 6, you get a remainder 0, right? Okay. So when you subtract, you get a remainder 6. Now another way to think of Z6, we talked about this the other day, Z6 is isomorphic to the integers mod the ideal generated by 6, right? So when we can take when we think about 8 minus 2 being a multiple of 6, then our 8 minus 2 would be inside that ideal generated by 6, right? So two cosets are going to be equal means that R minus S lives in I. That's what it means for those two things to be equal. We talked about that defining equivalence relation. Okay. Right? I wrote I. Why am I writing I? What am I representing here with I? Yeah, which ideal in particular? The kernel of phi, right? So let me write this off to the side so that I don't have to keep, make sure that we know that I is the kernel. All right? So R minus S is in I, but I is what we're calling the kernel of phi here. So what happens if I apply phi to R minus S? What does it mean to be in the kernel? The kernel is what again? It maps to 0. So this must be 0, the 0 in S. Right?
Why is it the 0 in S? Not the 0. Oh, because it maps from R.
Yep. Now what can we do on the left-hand side? Break it apart. And then move this to the other side. And you get phi of R must be phi of S. And that's exactly how we're defining our homomorphism, or our function. This is the definition of psi, right? So we put equivalent things in to the function. We got equivalent things out. So that's good news, right? So it's well defined. If you put the same thing in, you had to get the same thing out. That's what needs to be a function, right? So far, so good? Okay. All right, so we have a function. It's well defined. We have a function. Now we need to show that it's one-to-one onto an operation preserving. Well, how do you show something as one-to-one? What do you start with?
Two outputs show the same. Yeah. Two outputs show they came from the same input.
Good. Yeah, so the outputs are the same, show that the inputs are the same, right? This is a statement about the outputs being the same, isn't it? This is what the outputs are. Move it around. Hey, am I still pointing to the right things? Move it around. Use your homomorphism. That's what the statement is. And then get back to this, right? So literally, it's the exact same steps written in reverse order. Okay. So for one-to-one, we suppose psi of R plus I is psi of S plus I. I really should be writing kernel of phi, but we already established that we're equating those right this second. Then phi of R equals phi of S. Subtract to the other side to get phi of R minus phi of S equals 0. And now again on the left-hand side, we have a homomorphism. So I can pull the phi back out, if you will, unseparated. This is a statement about R minus S being in the kernel. And so since the R minus S is in I, we have R plus I equals S plus I. So it is one-to-one. So it's literally the exact same steps we showed for well-defined, just flip-flopped. That okay? All right. On to how do we show something is onto again? Yep, take it out, output, and find an input, right? So take something that's in the codomain, which is the image of phi, and find something that maps to it over here, right? So if we let S be in the image, what does it mean to be in the image? Yep. So there exists something in R such that phi of R equals S, right? It is an output of phi. That's what it means to be in the image of phi, right? There's something you can plug in to get S out. All right, so we're trying to show that psi, this other function that I just created, is onto, right? Well, if I know that phi of R equals S, and this is the function that we created, what coset of I, what coset of the kernel of phi do you think you might want to use to get phi of R out? To get S out, I should say. R plus I, right? I now have an R that gives me this, right? I have an R that gives me this. This is phi of R on this side. I better use R plus I on that side, right? So now R plus I is in R mod the kernel of phi, and psi of R plus I equals phi of R by definition, but we chose our R to be S. Or sorry, we chose our R so that phi of R is S. So we started with something in the output and showed that we found something that we can plug into psi and get that as our output. So it's onto. So it's 1-to-1. It's onto. We still need to show operation preserving. I may not left myself enough room for that second one. That's okay. So for operation preserving, we need to show that it breaks up over sums and breaks up over products. The elements in our quotient ring are cosets. So I need to show that it breaks up over a sum of cosets and a product of cosets. But how do we add two cosets together? What do we really do? Yep, exactly. We add the coset representatives, right? So R plus I plus S plus I is R plus S plus I. And now, according to the definition of psi, what does that equal? Phi of R plus S. Good. And what kind of object is phi? So how can we rewrite that part? Yep. And now, in terms of psi, what does that equal to? Psi, yeah. Psi. What I think everybody would say it. Is the the second operation preserving proof going to be any different? Just delete a plus sign, right? So how can you rewrite R plus I times S plus I? Yeah, so yep, psi of RS plus I, yep. Yep, psi, yep, I know. Too many Greek letters flying around. And then what is psi of RS plus I equal to? Yep, good, phi of RS. And then again, phi is a homomorphism, so we can rewrite that as good. And then that's going to equal good. Excellent. And so that shows that it's operation preserving. So we really do have an isomorphism here. Right. So that proves our first isomorphism theorem. Again, it helps us out because we are no longer required to show two things are isomorphic. We're no longer required to get a one-to-one onto function, which might be a little bit harder to find. All we really need is an onto function with the appropriate kernel. Okay. So let's do an example, another example with this. This is number 13 on page, actually it's in the next section, but didn't really fit in the next section, in my opinion, on page 166. It says, let I be an ideal of R, then the quotient ring R cross R mod I cross I is isomorphic to R mod I cross R mod I.
I don't know why, it's just so satisfying. Like, it's just so nice that it breaks apart. Like
Exactly, yeah, exactly. It is satisfying. It's great. So this kind of stuff why I go into algebra. I like it, yeah. It's fun stuff. All right. So the idea here again is not to try to find isomorphism directly. We ignore this and find a function that goes from R cross R to R mod I cross R mod I. Define that function, hopefully in the most obvious way. That's the idea. Okay, and then that function will be onto with that as its kernel. That's the goal here. Okay, so ignore this. Pick the most obvious function you can find, and hope that that's the kernel. That's where we would start. Okay. All right, so let's define our phi to go from R cross R to R mod I cross R mod I by what? Well, what are the objects in R cross R? What do they look like? What kind of things are they? Or they're ordered pairs, right? The first element, the first component comes from, and the second component comes from the second R. Do they have to be equal, or can they be different elements when you create ordered pairs? They can be different, right? So I might as well call it, say, R comma S, or R1 comma R2. I'm going to do R comma S because I don't feel like writing subscripts. Okay. All right. So that's what our input looks like. Let's look at our output. Again, I've got a cross here. So that means I'm doing ordered pairs again, correct? what are these things? What kind of rings are these? These are quotient rings, right? So I've got an element R and an element S in R, and now I've got sets of cosets generated by elements of R. So what do you think you might want to map this R to over here in this first component? R plus I, and this S is going to go to S plus I.
And in this case, the I is the ideal.
The ideal, yeah. Yep. Yep. In this case, it's whatever ideal we started with. Yep. So, like I said, I'm going to try to create this function as the most obvious thing I can think of, right? I've got this ordered pair. I want to map it to another ordered pair. Well, I know how to generate these cosets. I use elements from the ring to generate the coset. So I'm just going to use the element from each component to generate the coset that I want. Okay. Certainly, I don't have any issues with well-defined here. An element generates exactly one coset. So I can't have two cosets generated by the same element. I don't have the same issue I did before. So we don't need to worry about one-to-one. We get the isomorphism for free when we mod out by the kernel. I just need to show that it is surjective, it's onto, and show that it's operation preserving. Okay? It's the only thing we need to show. And then we'll figure out what the kernel is. Okay? All right. So onto, or surjective. Again, for surjective, for onto, we start with something in the codomain, something in where your outputs land. Well, our outputs land in R mod I cross R mod I. Elements in there are coset, comma, coset. So we'll start with an R plus I, comma, S plus I being in R mod I cross R mod I. What element in R cross R do you think is going to map to that particular ordered pair? R comma S. Yep. Then R comma S is in R cross R, and phi of R comma S equals R plus I comma S plus I. That was easy. It was onto by construction, basically. Again, trying the most obvious thing and see if it works. Don't try to be fancy. Try the most obvious thing. All right, operation preserving. I need to start with two elements in the domain and look at what happens with the function we defined with respect to addition of those two elements and multiplication of those two elements. Our domain, our ordered pair, as an ordered pair, set of ordered pairs in this case. So I need to start with two ordered pairs, and since I didn't use subscripts before, I didn't feel like using subscripts now, so I just kept going down the alphabet. So I picked RS and TU being in R cross R. Nothing special about the letters. You pick whatever you want. The first thing we want to do is, well, do the operation. What is R comma S plus T comma U? How do we add ordered pairs? Good. And then how we define phi, what is that equal to?
T plus I.
Good. And now we need to break this apart. But remember, when we add cosets, the way we add cosets is to add coset representatives, right? So in the first component, I can really think of this as R plus I plus T plus I. And the same thing in the second component, just with S and U. And again, I didn't leave myself much room for that one. Let me erase this so I'll rewrite it in a minute. Now, what can you do? Oh, look what we did from here. We went from here to here with these two ordered pairs, right? We went from this step to that one. Of course, we could have also gone from that step to that one, right? So what can we do here? Split it. Yeah, we can write this as R plus I comma S plus I plus T plus I comma U plus I. Oops, I got that backward. Sorry. No, I don't. I don't have it backward. Sorry. No, I don't have it backward. I thought I had it backward for a second, but I don't. All right. This just breaks back apart again, doesn't it? You're used to going from that last step to the previous step, but it works the other way around. And now what's the first thing equal to? In terms of phi, what's the first thing equal to? Good. And the second one is equal to? Good. And isn't that what we wanted? At least I hope that was what we wanted, because that was where we ended. Do we need to go through the multiplication, or can you change it for multiplication?
Yeah.
You can figure it out?
Yeah.
Okay. The only thing that's going to change in the entire proof is everything is going to change from a plus sign to a multiplication sign, except what? What's still going to be a plus sign? Yeah, the plus I, right? That's how we represent our cosets, isn't it? It's element plus ideal. So all of these plus I parts will be there. Everything else, though, will be a multiplication. Yeah. But anything that has a plus I on it is still a plus I. Okay. So I'll let you do that. All right. So it also preserves the second operation. Okay, so the other part then is I want to use the first isomorphism theorem to get the isomorphism. Okay, so I need to figure out what is the kernel of this homomorphism. Okay, that's what we need to ask ourselves: is what is the kernel? Say that again.
He wears a funny hat.
It makes chicken.
Yes. I don't know. I heard something about Colonel Sanders today, and he lived like the craziest life ever. I really encourage you guys to look up Colonel Sanders' life. He was like ridiculous.
If I find a Colonel Sanders fan fiction, I'm blaming you.
It was like ridiculous. It was like he worked, like it listed all the jobs he worked, and he was in like he like started working when he was 12. And it was like he did this and this and this and this and this, and he was terrible at all of them. And then it was like, and he like started it out of a gas station, and then like a competitor in his town like got mad at him for like selling food out of his gas station because he was like taking away his customers. So then like the neighbor Sorry, that's just, it's just funny that I literally saw that this morning.
That's really funny. Oh, it's okay. We're allowed to take excursions. I do that all the time. All right. What do we want the current, based on what we're trying to prove, what do we want the kernel to be?
0. An ideal. That's what I was looking for.
Well, a kernel's always an ideal. But for this specific problem, what do we want the kernel to be? Going back up to what we're trying to prove, it was why I scrolled back up.
Ordered pair.
It'll be a set of ordered pairs. Okay, so this is what we're trying to prove, right? This is the function we created. What do you think you might want the kernel to be?
0. Nothing.
Well, it can't be the empty set because 0 always maps to 0. So the kernel always has something in it. Compare the two things that I have written. What's missing in the second that's in the first? Ah, there we go. So what do you think we want the kernel to be? The ideal cross the ideal. That's what we want the kernel to be, right? Because remember, again, the first isomorphism says that first isomorphism theorem says that R mod the kernel is isomorphic to the image, right? We showed that this function is onto, so this is the image. So R, the ring, mod out by its kernel of this, mod out by the kernel of the homomorphism, is isomorphic to this. Okay, so I want this to be the kernel. So we want the kernel of phi to be I cross I. So I want them equal as sets. How do we show the two sets are equal? Typically, how do we show the two sets are equal? Yeah, their elements are the same, right? One's a subset of the other and vice versa. Let's do the easy case first. If I comma j is in I cross I, I wrote a really big comma. Then phi of I plus j is equal to, or excuse me, phi of I comma j is equal to what?
0 of the output. It maps to 0.
I don't know what's in the kernel yet. I want to show that it is in the kernel. Yep. I plus capital I, j plus capital I, right? I want this to be in the kernel. So what do I want those to be?
0.
0. You want it to be 0, comma 0, or 0 plus I, comma 0 plus I, because that is 0, comma 0 in that other ring. Okay. How do I know that this is 0 plus I, comma 0 plus I? Where do I and j live? In the ideal, right? I comma j lives in I cross I, so I is in I, so is j, right? When the element is in the ideal, that is the same coset as the ideal itself. Remember that two cosets are the same if the difference of the two elements is in the ideal. That's how we get two cosets are the same, right? Their differences in the ideal. Well, if I is already in the ideal, I minus 0 is in the ideal. So I and 0 are the same coset generators. They generate the same coset. So this tells us that I comma j is in the kernel of phi. So we've showed that I cross I is contained in the kernel. Now we got to go the other way around. Oops. Got chalk on my finger so I can't scroll, or it locked up again. There it goes. I wasn't scrolling with chalk on my fingers. Now let's start with something in the kernel. See, I hear Colonel. I think Colonel Sanders. I think of the South Park episode where the dog whisperer is training Eric Cartman and comes in with a bucket of chicken. And Cartman goes, "Colonel?" and tilts his head like a dog. That's what I think of every time I hear Colonel. But my mind is gone. It's fine. Sorry, Devin.
There are things that I know but don't remember, and that episode was one of them.
Yeah.
I watched that. I'd forgotten about it, and now the image won't leave my eyes.
I'm sorry. Chicken, Mom, give me a chicken.
As someone who's never seen that show, that just sounds crazy.
That was pretty on brand for the show too.
Yeah, it was. It is a little odd at times, but that was pretty fun.
Aren't they kids?
Yes.
Isn't it?
Mm-hmm.
Yeah, I just know it's kids and that they swear a lot. And sometimes say inappropriate things. But I've never actually
Oh, it's not sometimes say inappropriate things.
It's
It's always say inappropriate things.
I also noticed that in that one World of Warcraft episode, the guy that was the nerd who was beating them, that was a real dude.
Oh, yeah.
They were making fun of. He was one of the devs of Blizzard.
That's really funny.
And his son's a famous YouTuber now. Talking about that.
There's a good story because some celebrities want to do cameos, and of course they want them to do a cameo that's just kind of off brand, right? They don't want it to just be the person; they want to be something weird. Well, George Clooney did a cameo, and he was just a dog that barked.
Oh.
It was literally he just voiced over the dog barking, and that was it. That was his cameo.
Well, it's like Vin Diesel playing Groot.
Yeah.
He wanted to say the words
I am Groot. It's just weird. All right. Let's go back to some algebra. What does it mean to be in the kernel again?
It maps to 0.
It maps to 0. Good. So phi of r comma s is 0 plus I comma 0 plus I, right? But how is phi of r comma s defined? How do we define the function? Good. So we have r plus I comma s plus I is 0 plus I comma 0 plus I. And how are two ordered pairs equal? Good. So if r plus I equals 0 plus I, that's an I, looks like a J. What does that tell you? How are two cosets equal? It's on the board behind me. How are two cosets equal? Yeah, when you subtract them, they're back in the ideal. So where does R live? In the ideal. Where does S live? In the ideal. So where does R comma S live? In the ideal cross the ideal. Hence, the kernel is really I cross I. And by the first isomorphism theorem, we have R cross R. Oops. Mod out by I cross I. Oh my heavens. Oh, for heaven's sake, it's locked up again. I don't know why it's locked. It literally only locks up in this room. It's hope. I don't understand. Oh, now it's got it. Okay. Cross I. This is isomorphic to R cross I. Seriously, I teach 3 classes back to back, Monday, Wednesday, Friday. I literally have 0 issues ever with it. I come in here. It needs a break. It doesn't like abstract. All right.
Maybe it is the TV, actually. I said that jokingly, but that could be the common fact.
I guess it could be connected to the TV. It's not this. I bought the Switch so that I could switch back and forth between computer and laptop, but it was doing it before I bought the Switch, so it's not that either. It's not the Switch.
I know that the graphics drivers on my computer sometimes do not like it when I throw my screen to the monitor that's too big.
And this TV would be a lot newer than what the projectors in the classroom would be. That could be.
It also tries to default to the resolution of the TV. And sometimes you're.
Yeah, I didn't think about that. Maybe I should try to change the resolution and see what happens. Cool. Yeah, no, that's a good thought. I hadn't thought about that. All right. Questions on that one? Now that we got all the way through it. It was exciting, wasn't it? Seems like you all loved it a lot. All right. So let's keep going with the idea of quotient rings, but we're going to add in some new concepts. So in section 6.3, this talks about the structure of R mod I when I is prime or I is maximal. Now, of course, they just threw those words in here. It's because they've defined these words earlier in a different chapter that we didn't talk about. So I need to define what those terms mean for an ideal. Although you might be able to guess what it means. So, well, maximal, I hope, is fairly obvious. But let's talk about what we mean by a prime ideal. So by prime ideal, let's remember what we mean by a prime number. What does it mean for a number to be prime?
It can't be divided by any integers other than itself
and 1. Yeah, itself and 1. Exactly right. So when we do that with the integers, how do we know if an ideal is prime or not prime? Well, let's think about just the number. So remember, in the integers, we can generate every single ideal by a single element, right? We said that there's a principal ideal domain. Everything in the integers is generated by a single element. So if you look at the ideal generated by 5 versus the ideal generated by 6, what are the elements of each of these? Well, again, since it's a principal ideal and it's commutative and it has an identity, the ring is commutative and the ring has an identity, we know that this is just the set of all multiples of 5. And this is the set of all multiples of 6. Right? Do you agree? Okay. So let's think about how 2 elements can get in the ideal. Or sorry, let's think about how a product can get in the ideal. So again, another way to think about something being prime, if I have a prime that divides a product, prime, I used a P here. What has to be true if a prime divides a product?
Product isn't prime.
Well, the product isn't prime, but what has to be true about the factor P relative to A and B? If I have a prime that divides a product, what has to be true? Say it again?
It has to divide either A or B.
Yeah, so it has to divide one of the factors, right? So the prime itself is 1 or P. The only way I can get a P in a product is if it's in one of the it's in one of the things that's being multiplied, right? So this says that P has to divide A or P has to divide B. And it does have to do with the fact that the only factors of P are 1 and P. So if, remember, the proof is that if P doesn't divide A, then the GCD of P and A is 1. So you can write AR plus PS equals 1, and then multiply both sides by B. And so then P divides P, P divides A, B, so P then has to divide B. That's how the proof goes. All right, anyway. I have a prime divides a product, means that it had to divide one of the factors. Okay? So let's think about it in terms of the way the ideal is stated. What would happen if AB is in the ideal generated by 5? What does it mean to be in the ideal generated by 5?
I guess either A or B is a factor. Multiple. That's the word I'm looking.
Yep, that's where we're headed. That's exactly right. Okay. So just generally speaking, though, if something is in the ideal generated by 5, then it has to be 5 times something, right? We agree? So now we know that 5 divides the product. So that would tell us that either A is a multiple of 5 or B is a multiple of 5, right? That's what we just said about a prime dividing a product has to divide one of the pieces. Same idea, yes? Okay. Which tells us that A is in the ideal generated by 5 or B is in the ideal generated by 5. So if the product is in the ideal, then one of the factors is in the ideal. Let's look at the ideal generated by 6. Does the same thing work for that? Can you think of a product that's in the ideal generated by 6, but neither factor is in there? I want A, B is in the ideal generated by 6, but A is not, and B is not. Can you think of a product that'll work? 3 times 4? Sure, that works. 3 times 4 is 12, which is certainly in the ideal generated by 6. But 3 is not in the ideal generated by 6. And 4 is not in the ideal generated by 6. And you could have thought of other examples, right? 3 and 2 would have worked as well. $15 and $34 would have worked. All sorts of examples. Okay. All right, so notice that the prime number 5 generated an ideal where we've got this property that a product is in the ideal means one of the factors is. The ideal generated by 6, which is not prime, did not have the same property. So it's an extension of this property of how we define a prime ideal. So definition, let R be a ring. We're going to let R be a commutative ring. And let I be an ideal of R. Then I is prime if whenever a product is in the ideal, then one of the factors is. Okay, so generally speaking, in Z, the prime ideals are exactly the ideals generated by a prime number, or 0. We'll talk about that here in a second. But let's get a little bit more of an interesting definition, or an interesting example, I mean. Let's let R be your polynomials with integer coefficients, and let's let I be the ideal generated by X. Let's suppose that we have a product that is in the ideal generated by X. I want to show that either f of x is in the ideal generated by x, or g of x is in the ideal generated by x. But let's think about what the elements of the ideal generated by x is, or what that polynomials look like if it's the ideal generated by x. So we're taking any polynomial but multiplying it by x, right? So every single polynomial in the ideal generated by x has what for a constant term? 0, right? Because remember how we generate the ideal generated by x. We take x and multiply it by any polynomial, right? But if I multiply by any polynomial, that polynomial I'm multiplying by, I have a constant term, but I'm multiplying it by an x. So I'm knocking that piece up by a degree of 1, right? So we have no constant term. So let's think about what these products would look like if you have let's say your f of x is, let's say all the coefficients are a sub i's for the f and all the coefficients are b sub i's for the g. Let's say we had an a naught plus a1x, a2x squared, and so on up to some point, and then do the same thing with b's. What's the constant term in that product? A naught, B naught, and then everything else in that entire product, it has to have at least 1x in it, doesn't it? We agree? Everything else has to have at least 1x in it. So I can write this as x times some other polynomial. We agree? And we're trying to say that this is in the ideal generated by x. Agree? Okay. Well, if I cover this up, where does this thing live? In the ideal generated by x, doesn't it? That's exactly how it's defined, isn't it? Okay. So if this whole thing is in the ideal generated by x, and this piece is, what can I say about this?
Either 0 or also.
Yeah, in general, it has to be in the ideal, right? If I take two elements into that, I take two elements in an ideal and subtract them, their difference is in there, correct? So if this is in the ideal generated by x, and the whole thing is, I subtract them, and that has to be in there, correct? So this would imply that a naught, b naught is in the ideal generated by x. But that's a constant, isn't it? Are there any constants in the ideal generated by x? Just one. What's the only constant in there? 0. So it tells me that my a naught and b naught, when I multiply them together, I get 0. But what kind of objects, what kind of numbers are A naught and B naught? What kind of constants? What ring do they live in? What ring do they live in? Integers. How is a product of two integers equal to 0? Well, one of them is 0, right? So if this one is my F and this one is my G, if A naught is equal to 0, where does f of x live? Yeah, in the ideal, right? If B naught is equal to 0, then where does g of x live? In I, right? Okay. So this would tell us that f of x is in the ideal generated by x, or g of x is in the ideal generated by x. So we started with a product was in the ideal generated by x. One of them had to be in the ideal generated by x. Hence, I equals ideal generated by x is prime in z adjoin x. A little bit more of a non-trivial example there. Is that okay? We're going to play more around with these ideals, but let's do another definition. Because the other word we had was not just prime, we had maximal, right? So we let R be a ring. We'll do commutative. And let I be an ideal of R. We say I is maximal in R if, pardon me, for any other ideal J in R with J between I and R as a subset, we have I equals J or J equals R. I equals erase. No, stuck again. Stupid thing. We'll try a different computer next time. See if it. This might take several minutes. Great. That's what I wanted to do.
Oh, it's restarting. Insane.
Yeah, it did. Most of it. Let's see. And now it's locked up again. There it goes. All right. We have either I equals J or J equals R. That's what I was trying to say. There is no ideal that properly contains I and is properly contained in R. That's what it needs to be maximal. If I try to expand the ideal just by a little bit, it becomes the whole ring. That's what maximal means. So, to give an example of a maximal ideal, well, let's give an example of something that's not maximal. Let's go back to that. Now, let's start with maximal ideal first. In Z, all prime ideals except the ideal generated by 0 are maximal. Notice that the ideal generated by 0 is a prime ideal in an integral domain? Think about why. What's the only element in the 0 ideal? 0. If you're in an integral domain, what's the only way you can multiply to 0?
What are the elements in 0?
If you're in an integral domain, the only way you can multiply to 0 is if one of the factors is 0. And that's just another way to say that you're in the 0 ideal. So in an integral domain, the 0 ideal is always prime. Okay. Certainly, this is not maximal in the integers. We've got other ideals that are certainly bigger, right? But what we're saying with this is that everything else that's a prime ideal is maximal. Okay. Let's see why. If we have a prime ideal, P, that is the set of all multiples of P, right? Okay. I want to try to make it bigger. I want to add another element to it. Okay. The idea of being, if it's not maximal, it has to be properly contained in another ideal. Okay. So let's throw one more element in it. Let's say that the ideal P is properly contained in some ideal J. Then there exists, I'll call it X in J that's not in P, right? Which means X is not in the ideal generated by P. That's specifically what that means, right? If X is not in the ideal generated by P, is X a multiple of P? No. So P does not divide X, correct? Okay. Then what is the GCD of X and P? 1. Okay.
Okay, so we say that prime number and fraction can't be divided further.
Yeah. Oops. Pn. So if the GCD of X and P is 1, we can write 1 as a linear combination of X and P, correct? Where does X live? In J. Where does P live? Also lives in J, doesn't it? So where does XM plus PN live? In J. So where does 1 live? In J. What happens when a 1 gets in an ideal? It's the whole ring. Yep, it blows up to the whole ring. Good. All right, so then since X is in J and P is in P, which is a subset of J, we have XM plus PN equals 1 is in J, thus J is equal to R. And the ideal generated by P is maximal. Okay. So every prime ideal in the integers besides 0 is maximal. It's do another example here. We just saw that the ideal x generated by x in z adjoint, oh my goodness, in z adjoint x is prime, but not maximal. Why is it not maximal? Well, remember that this ideal generated by x has what for constants? But the constants in the ideal generated by x is 0, right? Right? So this is the set of all polynomials with 0 constant. This is, remember, the set of everything that you can generate by using multiples of x plus multiples of 2. So what is this, the set of polynomials? What's the defining characteristic for this set of polynomials? What's true about the constant? If I can take anything that's a multiple of x plus anything that's a multiple of 2, what's the defining characteristic in terms of a constant for this set of polynomials? The constant has to be what? Even, right? Which is certainly properly bigger than the things that have 0 constant, isn't it? And certainly not the entire ring. Okay. So this ideal is prime, but it's not maximal. Now it does turn out, we're not going to have time to prove it today, we'll do this on Tuesday. It does turn out that maximal ideals are always prime, but this shows that just because you're prime, it's not necessarily maximal. All right, so we'll play around more with this on Tuesday, and this will be the last section that will be on your exam. Okay. But again, we will take that exam during the week of the 11th, and you can take it any time during the week of the 11th. I don't care when. Now, I'm guessing you'll probably push it towards the end of the week versus the beginning, but generally speaking, that's what we'll do. All right? Does that sound like a plan?
Yep.
All right. So we'll finish this section up next Tuesday. We don't have class on Thursday. It's a full break. Okay. Finish this up on Tuesday. We'll probably get started in Chapter 7 as well. Depends on how Tuesday goes. All right? Have a good one, everybody. Have a good break.
You too.
Yeah, we're going to Wisconsin. Maybe we'll go to Door County.
I'll be here.
I'll be there. Good cheese.
Actually, I'm going home on Saturday. That's it.
I hope I can buy some good cheese. I'm a big fan of cheese.
There we go.
No.
No. You don't like cheese?
I love cheese.
I'm weird about cheese.
Cheese doesn't like me.
I love cheese, but like
Yeah.
I love.
You could have just stopped after weird.
Me too.
Yeah.
Oh,
I'm just
Dr.
teasing.
Joe.
I'm